Dear children, in this section we will be learning about two fundamental results in calculus without actually proving them. Instead, we will be using their geometrical interpretation. So here we go. Look at these two curves. You will find both the curves are continuous. If we take the interval from A to B, closed interval if we take, then the curve is not breaking anywhere and we find it to be a continuous curve whether we take this example or we take this example. So both the curves are continuous in the closed interval A to B. They are even differentiable if you see in the open interval AB. Even this one is differentiable in the open interval AB. And one more interesting thing can be observed here. The value of the function at A and the value of the function at B, that is equal. You can observe that here also. Value of the function at A is fa if the curve be taken as y is equal to fx, and at B the value of the function is fb. So you will find fa is equal to fb. Now if we make tangents at different points on both these curves, infinite tangents are possible. We can have various tangents in this part of the curve or in this part of the curve. In the same way here as well. All these tangents will be inclined at certain angle with the positive direction of x-axis. Either that angle will be acute or that will be obtuse. But in this case, if you see, there is one tangent which comes out to be parallel to the x-axis. In this figure, you will find there are two tangents which are parallel to the x-axis. So Rolle's theorem states that if we have a function, say f, which is defined from closed interval ab to the set of real numbers, say this be our function. So let this be a function which is continuous on closed interval ab and differentiable on open interval ab. What is the third thing we have observed here? Such that value of the function at b is equal to the value of the function at a. Now under this condition where you can see what are a and b, where a and b are some real numbers. Now under this condition you will find there will be a number within this curve, within this interval there will be a real number at which you will get a tangent which will be parallel to the x-axis. Now if these are the tangents which are parallel to x-axis, that means their slope will be equal to 0. Okay, so we can say that then there exists a real number c belonging to this open interval ab such that slope of tangent at the point C will be equal to 0. Now slope of tangent can be denoted as the derivative at that point. So this will be equal to 0. That is what is claimed by Rolle's. So this is our Rolle's theorem. The function has to be continuous in the closed interval. It should be differentiable in the given open interval. And if the value of the function at the endpoints they are equal, then you will be always able to get at least one point within the open interval where the derivative of the function at that point will reduce to 0. In this case you can see there are two such points. Let us explore another case. It is possible that value of the functions at the endpoints are not equal. So let us explore that condition as well. Now look at this curve. In this curve you will find This is the point A corresponding to this, capital A corresponding to this, the x coordinate is small a. Corresponding to the point capital B, the x coordinate is small b. So you can see the value of the function at A and the value of the function at this point B will not be same. If I assume the curve is, say, y is equal to fx, so you can easily see when x will be a, the value of the function at that point will become fa. And here x is b, so the value of the function at b is equal to fb. So you can see their heights are not same, their level is not same. So obviously fa here is not equal to fb. So what can be observed about this case? Again, you will find the function is continuous in the closed interval AB. It is not breaking anywhere, you can see. It is even differentiable in the open interval. Fine. And again, if we make infinite tangents over here, you will find something shared common, which will be common between those tangents and the secant or the line segment which is joining AB. So if you are asked to make many tangents on this curve, you will find there can be at least one point, more than one points are possible. So we can say there may exist at least one point where if the tangent be made, like you can see at this point C1, okay, corresponding to this, the point is denoted by capital P1. So at this point when the tangent is made, you can see it is parallel to this chord. Okay, so and chord, or we can say secant, we can call it a line segment. So how will we find the slope of this secant? You have learned how to find slope of a line segment when 2 points on it are given to us. So using that, the slope of AB can be obtained. And the slope of this tangent will be the derivative of curve at the point C1. So let us see what is geometrically meant by this condition. Again, say fx is our function from the closed interval to the set of real numbers, and we are assuming it to be a continuous function on the given closed interval a to b and differentiable in the open interval AB. Now under this condition only, we don't have that third condition here. Fine. So if these two conditions are fulfilled, we can say then there exists a point C belonging to this open interval AB such that, now if you compare with this curve, this number C has got two values. One is C1, another is C2. So you can see from the diagram at C1, the slope of the tangent, if corresponding to this a point is made out on the curve which is capital P1, you can see at this point the tangent is parallel to the line segment AB, and we are able to say that the slope of the tangent which is made at this point is equal to the slope of AB. So slope of the tangent at the point P1 which is having x coordinate C1, and here in general we have written C, will be f dash C. So this is the slope of the tangent. It should be equal to the slope of AB. How do we write slope of a line segment joining 2 points? It is difference of their y coordinates divided by difference of their x coordinates. See, corresponding to small a, the y coordinate is fa. Corresponding to small b, the y coordinate is fb. So this is what is being stated by Lagrange's mean value theorem. If you see carefully, this is a general theorem for Rolle's theorem also. We can say Rolle's theorem is a particular case of Lagrange's mean value theorem. What is happening in Rolle's theorem? FB and FA are equal to each other. The moment they become equal to each other, this reduces to 0. And the condition of Rolle's theorem is obtained. Let us check their applications. Let us see whether they are applicable in some of the cases or not. We'll verify it. Okay, look at this one. It says verify Rolle's theorem for this function. So you first look at the nature of fx. What do you find? Fx is a polynomial function. So we can mention fx is a polynomial function. And what do you know about polynomial functions? They are everywhere continuous. So we don't need to check if there is any point of discontinuity. We can write, therefore, fx is continuous on the given interval, that is closed interval -4 to 2, and differentiable on open interval -4 to 2. Fine. Now when we say it is differentiable on this interval, we can quickly check what its derivative will be. We will find f dash x will be twice of x plus 2. Now checking for the third condition, value of the function at b, that means the upper end. So if we calculate the value of the function at 2, you can replace x by 2 here. So this is square of 2 plus 2 times 2 minus 8. See what we get. This is 4 plus 4, 8 minus 8, which is 0. In the same manner, value of the function at -4. So square of -4 plus 2 times -4 and minus 8. So this reduces to 16 minus 8 minus 8. So that makes it 16 minus 16, which is again 0. So what do we see? Value of the function at -4 is same as value of the function at 2. So therefore we can say there exists C belonging to the open interval -4 to 2 such that f dash C is equal to 0. Now look at the derivative of the function. It is 2x plus x. So what is x now? X is the point C. So if we replace x by c, we get 2c plus 2 is equal to 0. And this provides us the value of c, which comes out to be -1. And you can see it belongs to the given interval, which is -4 to 2. So what do we find here? Rolle's theorem is applicable for this case. Children, taking another example, again we are going to examine whether Rolle's theorem is applicable for these two cases or not. So we have to always look at the functions first. What is in the first part? If you see, fx is a greatest integer function. What do you know about the greatest integer function? You can quickly recall. We know that greatest integer functions are not continuous. Okay, so fx is a greatest integer function and it is not continuous at which values? It is not continuous for x belonging to integers. So you need to look at your interval. Over here you can see x can be, look at your interval, it is 5 to 9. So let us see what are the integers over here. If I exclude 5 and 9, then also x can be what? It can be 6, 7, 8. See, from 5 to 6, including 5, and if 6 is not included, the function remains continuous. But the moment x becomes 6, the continuity breaks. The continuity breaks at 7. Continuity will break at 8. And here 9 is also included. There also the continuity will break. So x is going to take these integral values where the continuity will break, where fx is not continuous. So what is happening? The very first required condition is not fulfilled. So therefore, Rolle's theorem is not applicable. So it is not valid, we can say, in this case. Now look at the next one. it is a polynomial. We have done one such question. We can say fx is continuous on the given interval 1 to 2. This is the second part we are discussing. Also, fx is differentiable on the open interval 1 to 2. So first two conditions are met. Let us check the value of the function at the endpoints. So value of the function at 2 will become square of 2 minus 1. That comes out to be 4 minus 1, 3. And the value of the function at 1 comes out to be square of 1 minus 1, which is 0. So see, the third condition is not fulfilled. We can see f2 is not equal to f1. So again we can say Rolle's theorem is not applicable or is not valid in this case. So these were three examples of Rolle's theorem. We could see in one of them the Rolle's theorem was applicable, whereas in other two it was not applicable. Let us take some example of Lagrange's mean value theorem. See, again this is a polynomial given to us. So we know we have to check the applicability of mean value theorem here. So we know fx is a polynomial, and we can therefore say it is continuous in the given interval, which is closed interval 1 to 4. We can say it is differentiable. It is differentiable on open interval AB, which is open interval 1 to 4. And see what its derivative will be. F dash x will be 2x. We will be using it minus 4. Done. So therefore we can say, because the first two required conditions are fulfilled, we can say there exists a real number c belonging to this open interval 1 to 4 such that f dash c will be equal to value of the function at b minus value of the function at a over b minus a. Now f dash c we can obtain from here, replacing x by c. So it is 2c minus 4. fb and fa can also be evaluated. You can see that for finding fb we can replace x by 4. So when you will be solving for it, see, if I replace this by 4 we get 16, and this also becomes 16. So 16 minus 16 gives us 0, and we are left with minus 3. So FB is minus 3. Then moving on to FA, A is 1. So 1 minus 4, that comes out to be minus 3 and also minus 3. So minus 6. FB minus FA over B minus A. Let us simplify it. 2C minus 4 is equal to 3 plus 6 minus 3 plus 6 over 3. So you will find right hand side reduces to 1. 3 over 3, which is 1, which can be further simplified. Twice of c is 5, which means c is equal to 5 by 2. So you can see 5 by 2 belongs to the given interval, that is open interval 1 to 4. So we have verified mean value theorem is applicable here.